Guys, let's get started. So the first thing first, I was gonna go over the quiz two and solve the problem. Um, but nice. Can you get another sound check, guys? Sorry, I'm just always worried.
You sound good.
Okay,
Yeah, we can hear you.
Yeah.
great. Thanks, guys. So anyway, in terms of, I think you guys probably already saw my announcement about please follow the instructions and in like how you guys are turning in the quizzes. I had the instructions there for a pretty specific reason to use Gradescope. It's kind of a pretty regimented type of thing. And normally I'm pretty easygoing, but I don't like rules and stuff like that myself, and I'm pretty bad at following instructions. But I think it's something you guys should be like, if you don't learn how to do that, you're not putting your name on the tests, or you're not doing specifically what's being told, that you need to do. I think it's going to haunt you guys. So I'm going to like put my foot down starting quiz 3. And so like, you guys, it's not too many instructions for you guys. I think you should be able to follow it. And of course, many people did follow the instructions. So, and I'm sure the rest of you guys, again, like it's sort of nerve-wracking taking tests and stuff. And so, but just, now sort of be warned. So next time you'll be ready to do it. One of the things I'm sure was giving some of you guys problems is if you're trying to do sort of paper and pencil or pen and pencil or whatever you want to call it, and then take pictures of it. If you're going to do that, just make sure that you still like hand in, in this case it was 6 pages, hand in 6 pages. So even if you leave, blank pages blank, and sort of copy on your piece of paper that you're writing down, sort of more or less copy the formatting of what's in the quiz. I'm sure some of you guys don't have printers, or maybe don't have iPads or something to mark the stuff with. Any questions about that?
Professor?
Yeah.
So when I was doing the quiz, I did check for Gradescope, but I never actually had the assignment there. And so when I was reading your instructions, it said like email specifically. So I was like, maybe he didn't want Gradescope. So I don't know if that's like an issue on my end of it not showing up on Gradescope.
I had the same thing happen. That's why I'm a little confused right now when you said that, because I would have turned it in on Gradescope if I understood. I'm sorry.
Yeah. No, actually, Amber, like I think you had it fine if I remember correctly. So it's not a problem of you guys not putting it into Gradescope. As a matter of fact, like I didn't, like when you look at Gradescope, at least the instructions they give is that for tests, for whatever reason, seems like they prefer the instructor to get the tests and then input it themselves. So it's not a problem like inputting it into Gradescope. What was happening is I think a lot of people turned it in with fewer number of pages that left. So when I pull it into Gradescope, it gets confused. So I would have to go into the PDFs or whatever that people have turned it in as and insert pages and like separate out the problems. And then the second thing was happening, of course, like, not putting your name or something on there was also like an issue. So it wasn't a matter of like everybody who emailed it to me, that was what I wanted you guys to do. And that was not a problem. It's just I needed a certain number of pages to be in your PDF, then like have your names on every page. It just ended up being a lot of manual work for me. Sorry, Amber, what were you saying?
Okay, thank you for clarifying that.
Yeah. And it's not that I don't like you because you didn't follow whatever. It's just I feel you, but it's like something that we got to learn how to do. I wasn't good at it either. I'm still not that great at it, but you guys need to be good at it. Okay. Okay, so let's now look at a technical problem. I think we had, let's see, how come, what's going on? I'm so slow. Just give me 1 second, guys. Let me try to turn off. Why is this thing going up so slow? Well, just live with it. So this was the circuit that we had, I believe. This was 1K ohm. I'd given you guys the actual resistance values. So
did you forget the battery?
Oh yeah, thank you, thank you.
Yeah.
Okay, thanks. So this was a circuit. So the 3 questions was what was it? I think we wanted V in versus V out for ideal diode. Same as A for constant voltage. And I think I'd given you guys a VD on of 0.8 volts. And then C was V out versus time. For ideal diode. I think, by the way, I think generally everybody did pretty well. There was a couple of areas that a bunch of you guys stumbled, but I think in terms of coming up with the steps of looking at the input being very low and very high and telling you where the diode is and redrawing your circuit and so on, I think everybody did really well. So I think you guys got those key aspects. But I'll show you guys where a few of you guys stumbled on A, and then sometimes like there'd be issues, but then like the nature of the circuit would kind of save you on A, but then bite you on B or whatever. So so let's look at it first. So we had in A, we look at so the case where V in is very low, is very negative. And when it's very positive, V in is. So when V in is very negative, you would, this point, you're pulling this guy very low. So this point gets pulled very low, much lower than 2 volts. So this guy turns off. So basically the circuit that you end up with is an open switch. Okay, so this is one place where a few of you got so anyway, V out is equal to, in this case, V out is equal to V in. I think most of you did well up to this point, and then I'll tell you where you guys ended up like getting messed up over there. But and then the second case is where V in is very high. So when V in is very high, this point gets pulled high, higher than 2 volts, and then this guy turns on. But in this case, it's an ideal diode, so it just turns on like a switch, and you end up with a 2 volt battery thrown in here. Okay. And then let's say we want to figure out, so here in this case, So okay, so let's one place where I think a few people got confused here is they just did a voltage divider with a 2-volt offset as far as V out was concerned, which is understandable, but it's like I think you have to actually spend the time to figure out V in to V out. And the way I did it was so you got what the diode was supposed to do, but I think you went wrong in the analysis of this resistive circuit. So the first thing I would do is figure out what the current is. So this is my approach, but so from when the diode closes, the current is V in. So it's from here to here over these two resistors. So the current is V in minus 2 volts over R1 plus R2, or you could think of it as 2K. And then if you want to figure out the voltage at this point, one way to do it is just say V out is this voltage times plus the current going through R2. Okay, so V out is equal to V sub B plus I R2. So it's V sub B plus V in minus 2 volts, or I guess I should say keep it as V sub B. Minus V sub B, R1 plus R2 times R2. Okay, so if we plug in the R1s and R2s, we end up with V out is, let's see, is V sub B minus 1/2 V sub B plus 1/2 V in. Okay, everybody with me so far?
Yes.
Okay. And then, so you have these two equations, and where the crossover point happens, you have two lines. So where they equal is where the crossover point happens. So if I just say V out is equal to V in, like this guy. So Vn is equal to 1/2 V sub B plus 1/2 Vn. And then, so 1/2 Vn is equal to 1/2 V sub B, or Vn is equal to V sub B is the x-axis of the crossover point, and the y-axis of the crossover point, I guess it's easier to look at this guy, is just, so in the crossover point, both of these equations have to be true. So the y-axis, so this is x-axis, then the y-axis we could just use, again, we can just use this guy and get V out is equal to V sub in is equal to V sub B. So if I was going to draw it, which is the goal here, V in, V out. Okay, so the crossover point is at 2 volts or V sub B on the x-axis, and 2 volts or V sub B on the y-axis. Okay, so that's the crossover point. So before this point, the diode is off. And we basically have this circuit. Okay, so now you gotta, this is one place where some of you guys went wrong. You gotta draw, this is like your equation and you gotta trust it. And this equation basically says V out is equal to V in with a slope of 1. So it's just, so it's not gonna be like a straight line or something. I mean, it'll be a straight line with an angle, but it's like that's a line with a slope of 1 and no offset, right? There is no offset here. It's not getting clamped. So you just got to trust this equation and just plot it. Okay, so that's what you end up with. And then on this side, okay, you end up basically with, you know, we're looking at the slope. So if I look at the slope of this guy, V out is equal to 1/2 V in, or if you want to just draw it as R1 over R1 plus R2, or it's R2 over R1 plus R2 V in, and that's going to be your slope is 1/2, or we can put the resistor values in there. So that's what it's going to look like. Okay. Any questions there? This is
No, I guess what really tripped me up was I did the voltage divider myself because I guess I saw it done in my notes and I wasn't paying attention. But now that you do it, it makes sense, even just by looking at it.
You're talking about here and just doing a voltage divider, adding 2 volts to it?
Yeah.
Yeah, I think that's where a bunch of you guys went wrong. And I'm like, I'd do the same thing, but you just got to like try to be systematic. So anyway, but again, I'm happy because like, you know, resistive divider, you guys know that, you just got to be reminded. But I think in terms of the basis of the diode, you know, how you go analyze the diode circuits and all that stuff, almost all of you guys got to this point. And then where some of you guys went wrong is when you plotted this or plotted this, you didn't like, or sorry, plotted this or plotted this. You you didn't trust the you got to just sort of like follow what the equation said. It's just math. And then the second place where people went wrong was just in this resistive divider, and it wouldn't have bit you, like you would have been okay on problem A, but the problem is like when you look at problem B, now is the problem, because now you have so the same thing happens, right? You have, if you know, as V in is low, you have I'm not going to go through all the details there, R2, and the switch is off. But now you have, you know, you won't see it, but you'll have a VD on and a V sub B plus minus. So V out is equal to V in. And then V in is high. You'll end up with the diode on. Okay, so here we go. I love doing math. So I is V in minus VB minus VD on over R1 plus R2, and V out is VB plus VD on plus I times R2, or I'm just going to plug in the numbers. I think that's easier for me to keep track of. So VB plus VD on is 2.8 volts plus VN minus 2.8 volts over times 1/2, let's say. Hopefully that's easier to keep track of. Okay, V out. So so V out is 1.4 volts plus, sorry, I've got to put in this, plus 1/2 V in. So we do the same thing with the crossover point, make this guy equal to this guy. So crossover, let's not get lazy. So we just plug this guy in. So we get Vn as 1.4 volts plus 1/2 Vn. So then you end up with 1/2 Vn as 1.4 volts, or Vn is 2.8. So that's the x-axis. And the y-axis, V out, is equal to Vn for the y-axis. Oops. So the crossover point will be VB plus VD on, or 2.8 volts, and same with the y-axis. Y is equal to VB plus VD on, or 2.8 volts, and the slopes stay the same. So you'd have a slope of 1 and a slope of 1/2 here. Any questions about that, guys?
No, thank you so much for clarifying that, because I was a little confused.
Yeah. Oh, no problem. I don't blame you. Actually, I can remember your answers, Amber, but I would have gone down the same path myself. So, but I can't afford to do that. I'll be embarrassed in front of 30 people. Okay, so where you guys, a lot of people didn't do well is C. So basically, let me copy this over. A lot of you guys got really lucky, I tell you, because it was pretty clear you just picked your voltages right. So it's that also counts though. So what we have to plot is so if you basically, we want to plot V out versus time. So the way to do that is, like sort of put a time axis here, and then imagine, voltage sine wave. Input was, what was it, V0 sine of omega t or something, like a sine wave. And basically, was it cosine? Okay, thank you. So what I wanted to kind of see was that, and then, you kind of use that to see how that gets distorted by your waveform. So if you look at it here, as long as the input is below this V sub B, you have a slope of 1. So basically it just looked like a sine wave. And then as soon as you get over V sub B, you'll have a slope of 1/2. So you'll have a you'll have a cosine wave, you'll get a distorted cosine wave. So if I was going to plot it out sort of horizontally, so this would be time, and this would be voltage. Your input would look like, I don't know, like that. And then your output, as long as you are below V sub B, your output would look like that. It would look like that. So it looks like a sine wave. But as soon as you go over V sub B, you'd have this kind of you will get a slope of 1/2. So it'll look like kind of like this. Okay, and same over here. Oops. Does that make sense to everybody? Like
why is it 1/2? I'm a little confused on that bottom part.
On this thing?
Yeah. And why is it, like, I guess, limited?
So when you look at it, like, you got to kind of turn your head sideways here. So like so I took this. That's my input. Whoops. And I tried to paste it. Boy, that didn't work too well. Let's see. I'm trying to draw that. Mm-hmm. So if you look at it here, so this input, it's like I'm putting this input, I'm multiplying it by this curve. As long as this input is below 2 volts, so anywhere here, as long as I'm anywhere out here, I just multiply this input by a slope of 1. So you got that, right? So that's this part. So everything gets multiplied by 1. So if you have a cosine in, you end up with cosine out. Mm-hmm. As soon as you go above this point, so above this guy, now you multiply your input by 1/2, because that's your slope here.
Oh, I see what I did. Okay, now I understand.
Yeah.
Thank you.
So this is just this is basically 1/2 cos omega t slope in that area.
Okay.
So I think everybody, I think it makes sense. You guys didn't probably in the homeworks and stuff. I think there was less of this kind of look at circuits. So a bunch of you guys got lucky, but be careful. Now I'm gonna try to catch you in the final or whatever. Is if you just assumed you had like I didn't give you an exact value for V sub 0. So if you'd assumed V sub 0 max is 2 volts, like you'd never get above this curve. So you just get a sine wave. And so, but hey, it's correct. I can't argue with it.
Professor?
Yeah.
So what would be the break point?
The break point for this one, because I'm asking for the ideal diode model. So this is the same breakpoint as breakpoint as A, which was 2 volts on the VN.
Okay, so then so I was just wondering, because on the grade scope it says that I have the incorrect slope after and before breakpoint, but I believe I did have the correct one before the breakpoint, because what I did was basically I created the sine wave, but right after 2 volts, I like dropped it a little bit so that, because the slope obviously changes. And then, so yeah, I did that.
Okay.
So I was just wondering why that was.
I can't, sorry, Agav, I can't remember your test. So could you maybe like ask for a regrade or something? I don't know if you can do that for Gradescope, or just shoot me an email and I will look at your test.
Yeah, there's a request regrade actually, so I'll just click that and then.
Okay, great.
Yeah. All right, cool. Thank you, Professor.
Sure.
Professor,
Yeah.
what's the max score we could have gotten?
It's a maximum score of 3.
So because on the grade it doesn't have like a out of how many, so it's 3. If you have a 3, it's the max score we could have gotten.
Yeah.
Okay, thank you.
So at the at the end, I'm just going to multiply it all by the weights of the percentages and stuff.
Okay, thank you.
Sure. And again, I was pretty happy with like what all of you guys did on this test. So I thought it was, most everybody got sort of like the key aspects right.
Professor, can you scroll up a little bit to the end of B, please?
Sure.
Just wanted to make sure I had something. Oh, yeah, right there. Perfect. Thank you.
Sure. Do you want me to keep it there?
I'm just going to screen cap.
Okay.
Okay, I'm good.
Okay, great.
Yeah,
Okay, guys.
I was looking at it, and if I actually took a second to actually look at my circuit instead of just doing math, I guess I probably would have seen that. I guess I jumped too quickly on the math, and yeah. So that's pretty cool though. That if you actually analyze the circuit and if it's simple, you can clearly see where the breakpoint's at.
Yeah. Yep.
Thank you, Professor. Appreciate that.
Sure. Yeah, it's like, I was talking to somebody else, one of you guys, in office hours, and so the whole discipline of this kind of circuit design is kind of like half math, half sort of recognizing what might happen, or coming up with like theories about what might happen so you can check it with your math. But it's kind of like half and half, because this is one area, if you didn't do your math, with a bunch of you guys stumbled here with like a voltage divider kind of thing. So unless you do pretty disciplined math, it's not difficult math, but you got to be like, just don't jump to conclusion, don't jump steps and go through every step. If you didn't do that, you would have gotten it wrong. But you got to have like sort of a feel also for what's going on. So it's about half and half. And I wish I had like any better way to tell you guys how to get that, except just like solving problems. So I would, if I were you guys, I think again, you guys are doing well, but if I was just keep giving you advice on how to do it, is listen to the lecture and then jump straight into the homework, and then like start reading the book or something like that, or re-look at the lecture once you're like run into problems while solving the problems. If you like get stuck, then go back and see what the book has to say. But like the real important thing in this class is just solving problem after problem. And I think gradually you start getting a feel for this math versus recognizing sort of structures or what might happen. And we won't get into particularly difficult or complex circuits in this class, but as the circuits get more complex, I think last time we looked at like the schematic of an operational amplifier with like, I don't know, whatever it was, 20 transistors or something. So there, like, it gets more and more important to use the combination of math and sort of visual or sort of recognizing structures. And the only way to do it is just solving problem after problem, unfortunately. Unfortunately, if you don't like solving circuit math problems.
Oh, thank you. I appreciate that.
Sure. Okay, guys. So if there aren't any more questions, and again, if you have regrades, record requests, don't be shy. Ask for them on Gradescope. I have a few, unnamed people without their names on the test. I'll go ahead and do some detective work and get you guys sorted out. So you guys get your grades. I just haven't ran out of time to do that. But and then just lastly, again, just be sort of next time, just like follow the specific instructions. It'll help everybody out. Okay, all right, guys. So let's keep going on the bipolar. Let's see, 27. So I think where we left it was we have the bipolar forward active region. And then we have this, what's called the large signal model, because you guessed it, we're going to later on talk about the small signal model like we did on a diode. But the reason it's like what the large means here means the same thing as it did on the diode, means that you can basically use this model. So let me just draw it first and I'll describe what it means. So basically we had a voltage controlled current source, 3-terminal device. This was the collector. This was the emitter. This I sub C was I sub S exponential of VBE over VT. And then this was base. So sort of by definition, this is the base emitter voltage. And then to model the base current, we added a diode between base and emitter, and we made that diode's sort of leakage current, or I sub S divided by beta. So it's the same. It's the same I sub S as the collector, except divided by beta. Because if you guys remember, the relationship between I sub B was I sub C divided by beta. And then beta was between 50 and 200. Those are sort of reasonable numbers for beta. So to emulate that, we have a diode there with that exponential of VBE over V sub T. So what does that mean? You have this collector current, again, exponential of VBE over V sub T. You have your base current, which is the collector current divided by beta. And then you have the emitter current, which is the collector current plus the base current. Okay. And so the reason we call this, so back to why we call this the large signal model, just as a reminder, we had the same thing in the diode. The reason for that is once you're in the forward active region, this becomes your large signal model for the forward active region. Other regions would have their own large signal models, but once you're in the forward active region, you can basically use this model to fully describe your transistor behavior. Okay, so regardless of how big your signal is or anything, or what funky business your signal does, you can use this large signal model. But the large signal model has one big problem, and it's that it's complicated mathematically. So it has these sort of exponential terms in it So once you've got, a bunch of bipolar, we'll sort of see in the next, mostly in the next chapter, you got your bipolar transistor, you throw in a couple of resistors and et cetera, then it gets really difficult to solve when you're doing KCL, KVL with, exponential terms. So, so the small signal does the same thing we did with the diode on the small signal, which is, when you have a very small excursion on your input or a very small swing, then you can, instead of using this exponential model, we do an approximation, a linear approximation. Okay, but anyway, so this is where we are. This is the large signal model that basically describes the bipolar transistor for now. And then the other thing we said was that the steps to calculate the currents was that you'd figure out VBE, then from VBE you'd go to I sub C, and then this is basically I sub C is I sub S exponential of VBE over VT. And then once you have I sub C, you can go to I sub B, because I sub B is just I sub C over beta. And once you have I sub B and I sub C, I sub E is just equal to the sum of I sub C and I sub B. Okay, so that's your large signal model. And okay, I think that's what I want to set in there. And so now let's look at an example. Okay, this is example 4.7. And they're giving us a circuit. Bipolar transistor with a VBE of 800 millivolts. And the resistor is 500 ohms. And V sub C is 2 volts. And I sub S is 5 times 10 to the minus 17. Whoops. VBE is 800 millivolts, and beta is equal to 100. So question 1 is calculate currents and voltages. Okay, so why don't you guys take a shot at it, see what you can do. So just as a reminder, this is what you want to do to calculate the currents. Okay, you have, the problem has given you V sub B, VBE. Okay, we're giving you that. And then from there, you should be able to calculate I sub C. And from there, you can calculate I sub B and then I sub E. And then once you have I sub C, so in terms of the voltages, V sub BE gives you the voltage of the base, emitters at 0. And once you have I sub C, you have V sub C, so you can do a KVL and figure out what voltage is on the actual collector. So why don't you guys take a shot at that for a few minutes, and then we can look at it together. Okay, guys, let's give it a shot together. So the first thing you do is figure out I sub c, and that's just I sub s exponential of VBE over VT. We have I sub s from here. We have VBE, and V sub t is 26 millivolts. So this is 5 times 10 to the minus 17 amps exponential of 800 millivolts over 26 millivolts. And that's equal to 1.153 milliamps. Okay. So once we have I sub c, the next step to get I sub b is just to divide the I sub c by the beta. So I sub b is equal to I sub c over beta. So the problem gives you a beta of 100. So it's just equal to 1.153 milliamps divided by 100, and that gives you 11.53 microamps, which, by the way, this also shows you guys again what to kind of expect in this mode where your base current is much, much smaller than your collector current. So it's 2 orders of magnitude smaller on the base, which is something that's pretty attractive for the bipolar transistor. And then once you have the base and the collector, you have your step 3 here, which the emitter is just the sum of those. So 1.153 milliamps plus 11.53 microamps, so is equal to 1.165 milliamps. Okay. And then lastly, we want to figure out the collector. I did a bad job of labeling this. Well, let's just do VCE. Let's call it collector emitter voltage. Okay. So that would be the voltage at this node, which would be this V sub C of 2 volts minus the voltage drop across this resistor. You have I sub C, so you'd get V sub C minus I sub C times 500 ohms. It's 2 volts minus 1.153 milliamps. Times 500 ohms, and that's 1.42 volts. So at this point is going to be 1.42 volts. And then incidentally, you can double check. So having VBE at 800 millivolts already tells you the base emitter voltage is forward bias. We assumed, the sort of the implicit assumption in all these calculations is that the transistor is in the forward active mode. So now we can come back and see if it's that reasoning is at least internally consistent. So if this guy is sitting at 1.42 volts, like we just calculated, so 1.42, yeah. Then the base is at 800 millivolts. This collector is at 1.42 volts. So this collector base junction is indeed reverse bias, and it's reverse bias by 623 millivolts. Okay, so the collector base voltage is equal to 623 millivolts. So we are in forward active. So a lot of time what happens is, you design your circuit and then you kind of screw something up and you take it out of this forward active mode, and then you notice the currents aren't following your equations and all that stuff. What you have, as in on the bench, or what you have physically isn't following your currents, or what you have in Spice in the simulations isn't following your calculations. And a lot of times it's because you did something to take the transistor out of the bias condition that made it operate in this forward active region, or whatever region you were intending it to be. So it's good to go back and double check. Okay, so the next question, part B of this. Any questions about that? I think it's hopefully pretty straightforward. So part B is what is the max? So this is R sub C. Whoops. This is R sub C. So the question is, what's the maximum R sub C where the transistor is still in forward active? So basically what we've said so far is you want this junction to be, the higher the value of R sub C, the R sub C is not going to affect I sub C, right? I sub C is just a function of VBE. Okay, so the higher the value of R sub C, the lower this collector voltage is going to drop. At some point, it's going to drop low enough that the collector base junction is no longer going to be a reverse bias. And then basically you no longer have a forward active transistor. So the condition we're looking for is a case where this voltage is zero. The difference between the base and the collector is zero. Okay, that means that this point, if it drops to this collector point, if it drops to 800 millivolts or below, this transistor will no longer be in forward active mode, because this junction, the collector base junction, will not be reverse bias. So basically, you look at the case where minus 800 millivolts. So this is the minimum collector voltage that keeps the transistor in forward active. And so we want to set that equal. I sub C is going to be the same times R sub max. That's the highest value you can have. Okay, so I sub C is still 1.153 milliamps. And anyway, so this gives us our R max of 10410. Okay, any questions about that?
No.
Okay, great. So notice a couple of things. So we said, remember when we started talking about the bipolar transistor or transistor circuits, we said if you had a voltage controlled current source, voltage controlled current source, and you put an external resistor here, you would get gain. Okay, and then the equation for the gain was, this let's say this current was K times Vn, sorry. So the gain, it would be sort of minus K times R sub L. Okay, so this tells you that you want to make R sub L to get the highest gain. You want to make R sub L as big as possible. Okay, the more R sub L, the bigger R sub L, the more your gain, which is usually pretty desirable. Like, you basically not pretty desirable. You always want, well, almost always you want as high gain as possible. So anyway, but you see a limitation here is once you have a certain voltage supply in your circuit, if you make R sub L or R sub C too high, then you take your bipolar transistor, your transistor out of the correct bias condition. So that sets a limit for each voltage supply. You're going to have a limitation on the maximum R sub L that you can use for a given collector current. Okay, so and then you could say, well, why don't I just increase my supply voltage? So then I can just keep indefinitely. I'll make this guy, 3 volts, 4 volts, 5 volts, 10 volts, 20 volts, whatever it is. And I keep increasing R sub L to just get higher and higher gain. So that's, something pretty simple you can do, which get higher and higher gain by increasing the supply voltage and keep increasing R. The problem is basically you are linearly increasing your power consumption, because the power consumption of this circuit is this 2 volts times your collector current. And as if this guy was, if this guy goes up by a factor of 2, your power consumption of the circuit goes up by a factor of 2. And power consumption is usually something that's important for your customers. They want it as low as possible, or whoever's, for you. You want to slowly discharging battery on your cell phone or whatever. You don't want your computer to heat up your room, or the fan to constantly be going on your laptop. So basically you have this limitation on this gain, because usually you have a limitation on power consumption. Okay. All right, so that tells us that. So now let's look at the IV characteristics. So so far, up to the point of the transistor, every device you guys had seen were, there were 2 terminal devices. So, if they're resistors or diodes or whatever. So there are 2, basically you have, 2 terminals, one on each end. Means that if you want to look at the voltage versus current characteristic, one graph was going to suffice, because you had one voltage, or if it's a resistor, V sub R, and you had one current going across. Okay, now we're talking about 3 terminal devices. So we don't have just a relationship between a current and one voltage, but we're looking at the relationship between current and multiple voltages. Or also, you don't have one current, you have 3 currents. So you could plot like the current versus voltage characteristics, I guess, in a 3-dimensional plot and end up with a single plot, but that's, usually not, usually we have 2 dimensions, or paper or whatever that we're working with. So what you do is you basically look at your devices using 2 plots, the current versus voltage characteristics. So but they both have the collector current on the y-axis, but one of them is plotting that against the base emitter voltage, and the other one is plotting it against the collector emitter voltage. Okay, and what's implied here, because looking at it here, you're not looking at, there's no indication of collector emitter voltage here. So this is assuming that you are holding that VCE is equal to constant. Okay, and conversely, here on the right, there's no mention of VBE in this VCE versus I sub C graph. So here you are assuming that VBE is constant. Okay. Practically speaking, let's say if you were going to do this, make these plots in the lab, say, what you would do is you would take your transistor. So for example, for this plot on the left, so let's say your transistor is called Q1. So what you would do is you would put a battery or a constant voltage on VCE, and then you would put a variable voltage on VBE. So for each VCE, you would hold this constant, and then you would change this. Okay, you change this and you plot I sub C. Okay, hold this constant, change VBE, and see how I sub C changes with VBE. So this is for this plot, I sub C versus VBE with constant VCEs. And then same thing you would do if you were going to do this for VCE, you would now hold VBE constant, and you would vary VCE and measure I sub C and plot it. Okay, so let's see what would happen if you plotted. Well, so I sub C is I sub S exponential of VBE over VT. So it means that, we'd get an exponential curve, kind of like what our diode look like. Okay. And nicely enough, there's also, this is not the same, it's not true for every transistor. And also, as the bipolar model, we'll see like second order effects, you'll see VCE creeping in. But at least for this equation here, notice there's also no mention of VCE. Okay, which means that...
Professor?
Yeah.
Sorry to interrupt, but what's Q1?
Oh, this is the name of that transistor.
Okay. Thank you.
Sure. So by convention, so we'll be looking at 2 types of transistor in this class. One of them is the bipolar transistor, and the other one is the MOS transistor. We'll look at a little bit later. But for whatever reason, all the bipolar transistors, their names start with Q. And, if you're like running SPICE simulations, etc., you'll see, you'll name your bipolar transistor Q whatever. And then all the MOS transistors, they always start with M. So that's Q is just the name of it. Thanks for asking that question, though. But I'm just sort of like trying to sneak that in. Start calling these transistors Q1 through whatever. Okay, so VCE held constant, but in it, like no matter what we did anyway to VCE, whoops, didn't want to erase it. No matter what, VCE is not this equation, so you end up only with one graph. But it's not the case where different VBEs happen, because remember that, I mean, the same equation holds. So if I was going to hold VCE constant, sorry, if I'm going to hold VBE constant and change VCE, remember that we get this, you know, a constant current up to a point where VCE, you know, basically you're no longer reverse bias. So up to a certain point, you get a constant current. But then depending on, so this is for a certain VBE, let's say is VBE1. Okay, but if you, for different VBEs, you're going to get drastically different I sub C's. So if you had another VBE, so if you had a VBE2 that was higher than VBE, two was bigger than VBE1, oops, you would get a curve like that. Okay, and this curve would be I sub S exponential of VBE2 over VT, and this guy would be I sub S exponential of VBE1 over VT. So basically you end up in a situation where you know, you have multiple curves in your IC versus VCE graph, depending on where VBE is, depending on the value of VBE, but you only have one curve in the IC versus VBE curve, graph. Okay, so let's do one more example, and I think we can end it there, which is to, so basically it wants us to plot, so it's example 4.8. So with a bipolar transistor with I sub S of 5 times 10 to the minus 17 amps, beta of equal to 100, sort of create the IC, VBE, IC, VCE, IB, VBE, and IB, VCE curves. And do it for VBE of 700, 750, and 800 millivolts. Okay, it's not too bad because, you know, think of it that once you have a certain IC versus VBE, the IB versus VBE curve is just the same curve divided by the beta. Okay, same with once you have IC versus VCE, your IB versus VCE is just, you know, same curve divided by the beta. So basically you have two curves to really work through, is IC versus VBE and IB, sorry, IC versus VBE and IC versus VCE. So why don't you guys give that a shot, like give you a couple of minutes, and then I'll we can work it together. Okay, guys, so let's try doing this thing. So VBE. So first to do the plot of VBE versus I sub C. So we do a bunch of like different calculations for different VBEs. So like I mentioned, 750 millivolts, and VBE is 800 millivolts. Oops. So for each one of these, we do a separate I sub C calculation. So first 700 millivolts over 26 millivolts. This one is exponential of 750 millivolts over 26 millivolts, and so on. And so this is 24.6 microamps, 169 microamps, and 1.153 milliamps. So if I was going to plot this guy, so VBE versus I sub C, you would end up getting, you know, sort of an exponential plot. Notice how these are going up very quickly here. So these guys are stepping linearly, 700 to 750, from 750 to 800 millivolts. Each one of those is, you know, 50 millivolt step, but the currents are changing exponentially. Okay, so you'd end up with like, I don't know, like this would be 700 millivolts, and this would be 24.6 microamps, and then 750 millivolts would be out here. Then you'd have 169 microamps, and then 800 millivolts would give you 1.153. And, you know, I sub C here is, you know, we're probably drawing it on a log scale here to look like this, but you get the idea. So, and then I sub B, once you have that, I sub B is pretty easy because I sub B is just equal to I sub C over beta in each case. So you would end up with the same curve. Let me cheat here and just copy it. And I was just going to plot I sub B. All these guys would just be a factor of 100 less. So instead of being 24.6 microamps, it would be 0.246 microamps. And then this would be 0.169 microamps. Oh, did I do this right? Wait a minute. Oh, that's 0.0, sorry. So this is 0.0246 microamps, 0.169 and 11.5 microamps. So I sub B would have the same shape as I sub C, the curve of versus VBE, each one, but I sub B is a factor of 100 or a factor of beta less in value. Okay. And the curves for, I'll just plot this one here, for VCE versus I sub C would just be a bunch of straight lines, horizontal straight lines, one for each VBE. So for VBE is equal to 700 millivolts, you would end up with 24.6 microamps. And for V sub BE of 750 millivolts, it'd be 169 microamps. And for VBE of 800 millivolts, it would end up at 1.153 milliamps. Okay. Any questions about that, guys? Okay, if not, I guess I'll just stop here, and I'll see you guys on Thursday, or talk to you guys on Thursday.
Professor, can I just see the last graph, please?
Sure.
I got it. Thank you, Professor.
Sure.
Thank you, Professor.
Thanks. Take care, guys.
Thank you, Professor.
Bye.
Professor?
Aaron, did you have a question?
Yeah.
Okay.
On, I think Blackboard, I don't think you put what the quiz is out of, because I just got the points, but without like a total point.
Oh, okay. Yeah, the quiz is out of 3 points.
All right.
Yeah.
Okay. Thank you.
Sure thing.
Thank you, Professor. Have a good one.
Take
Bye-bye.
care. Bye.
I think I have the same problem about the grade, because my grade on the Blackboard didn't change. Like it's still the same after the last grade of the quiz.
What do you mean?
Let me double check in a second. Because I think it was like I had a problem on the Grayscope as well, from the first quiz. So I don't know if it didn't reflect on my Blackboard. I don't know if it has the same problem right now for quiz 2. Because it's only 2 quizzes, right? And like,
Yeah.
I got 2.75, and on Blackboard it says I have an F in the class.
Oh, well, it's not. Don't look at the grade, because I don't think it's like multiplying by the weighing and all that
Oh,
stuff.
I see.
So at the end, I'm gonna just like weigh the quizzes and the final and all that stuff.
All right. Thank you.
Yeah. Okay.